So today we want to look at the idea of impulse and momentum. So quick review. Momentum involves mass and velocity, and we could think of momentum as inertia in motion. We calculate the momentum by taking the mass and multiplying it by the velocity. This little symbol right here, the arrow on top of the velocity, reminds us it's a vector, which means the direction matters. We have to worry about which way it's going. And therefore, because velocity is a vector, momentum is a vector. Okay? So if momentum is mass times velocity, we can find changes in momentum by taking the final momentum minus the initial momentum. So if there's something going on and a bike speeds up, you can find the final momentum, you can find the initial momentum, and you can find the difference between the two. That's the delta P, the change in momentum. We're going to use that definition today. All right, so I'm going to skip through this because this is the example we did last time, finding the change in momentum. And so in this example here, I just want to point out that the change in momentum is always mv final, because this is the final momentum, minus the initial momentum. So when we say change in momentum, we can also write it as mv final minus mv initial. And that's what we did when we solved this problem. We were trying to find the final velocity of the baseball after it hits the bat. So this was the example from the other day. Okay, so that gets us to the new stuff, which is this idea of an impulse. So if you want to change the momentum of an object, what do you need? So let's say that you've got a kid on a bicycle and they're sitting still and you want to make them go. Well, in order to make them go, you have to apply a force. But how much you change their momentum depends on not just the force, but also how long you push on them. So if you push on them for longer, you'll change their momentum more than if you push on it for a short time. So this combination of forces acting for time is what is needed to change the momentum of a system. And the force that acts for a certain amount of time, we call that an impulse. It's really just a restatement of Newton's law. This isn't new physics. This is just another way to think about Newton's law, but it's useful for objects that interact. So a force acting for some time is called an impulse. And the impulse has units of newtons seconds. So force is newtons, time is seconds, newtons seconds. So here is what the equation looks like. The impulse is the force times the time that it acts. So we use delta t here just to mean the amount of time that goes by from the start to the end. And the force times the time is equal to the change in momentum. It actually causes the momentum to change. And we know that the change in momentum can also be written as P final minus P initial. Okay? So here is what the equation looks like if I just take out the first part of it here. An impulse, the force times the time is called the impulse, causes a change in momentum. So F is the force, it's measured in newtons. Delta T, or just T if you want, is the time that it takes to apply the force. And delta P is the amount of change in the momentum. It's mv final minus mv initial. So some examples, you may know that if you jump off something high, when you land, you don't lock your knees. You bend your knees, right? So when you jump off a chair, you bend your knees. What you are doing instinctively is making the collision last longer because your momentum is going to change. So if you can make the collision with the floor last longer, if time is bigger, then the force is smaller. So same idea if you're pushing somebody on a bike. You can push with a big force for a short time, or you can push with a smaller force, but you can push for a longer time, and both of those will change the momentum of the bike. So there's a trade-off between force and time. So for a constant change in momentum, the force and the time are inversely related. You can have a big force act for a small time, or a small force act for a big time, and both of those could do the same job. So here's an example. If a person has a mass of 100 kilograms and they're going 60 miles an hour, and we need to bring them to a stop. So let's say they're riding in a car. They're going 60 miles an hour, and they've got to come to a complete stop. We have to change their momentum. So to figure out how much we have to change their momentum, we take mv final minus mv initial. Now, if we're going to make them stop, the final velocity is 0. So the change in momentum will just be 0 minus the mass times the initial velocity, which is 2,600 kilogram meters per second. This is the change in momentum. And in order to change the momentum, we have to apply a force on them. And that force has got to act for some time. So here's some options. We could apply a fairly small force on them of 520 newtons. And if that force were to act for 5 seconds, that would produce the needed change in momentum. If you take 5 times 520, you get 2,600. Okay? So this would be like you're moving along in the car and you hit the brakes, and the force on you is you putting your hands on the steering wheel, which pushes back on you. And you stop pretty quickly, but that's only 5 seconds. Okay? Now, we could have a bigger force that acts for a smaller amount of time. If the force was 2,600 newtons, a bigger force, it would only have to act for 1 second, so that the force times the time would be 2,600. So this might happen if, for example, you hit a telephone pole and the airbag inflated and your seatbelt helped you, and your collision lasted an entire second. Okay? If the time gets smaller, though, the force gets bigger, because remember, the product of the force and the time have got to equal 2,600. So as the time gets smaller, the force gets bigger. And if you are not wearing a seatbelt and you get ejected and hit a brick wall, the time will actually be really, really short, but it'll be an enormous force, and this force is big enough to kill you. So the way airbags work is they apply a smaller force for a longer time on you, which changes your momentum. So an airbag might make your collision with the car, the slowing down and stopping, last an entire second instead of 1/100th of a second or even 1,000th of a second. And both of those reduce the force. So that's an example of how we change the momentum with different forces. So here's the big idea, and this is in your toolbox. The force times the time it acts is called the impulse, and the impulse causes the momentum to change. So we call this the impulse momentum theorem. Okay? So a force times the time causes the momentum to change. So let's just do 2 examples, and this is what you're going to be working on in the problem set. But pay attention just for another minute. There's a couple subtle things here. So here I have a force of 800 newtons. It's applied by a golf club for 5 milliseconds, or 0.005 seconds. The ball has a mass of 46 grams, and it's initially at rest. What will be the final velocity after this force acts? So I'm just going to draw a little diagram. I got a golf club applying a force on a golf ball. Here's my variable list. I have force and time, and then I have masses and initials and final velocity. So these are the 5 variables we're going to have when we're solving problems with impulse and momentum. Okay? Now, once you read the problem, you can probably figure out that the force is 800 newtons. The force acts for 0.005 seconds. The mass is 46 grams, which we'll convert to kilograms, so 0.046 kilograms. And the initial velocity is 0. We're trying to find the final velocity. So this impulse momentum is a principle. It's an idea. We apply it to this problem. That means F times t equals the change in momentum is mv final minus mv initial. We are trying to solve this equation for v final. So that's our plan. I'm going to try to get v final by itself. So first of all, since the initial velocity is 0, that term gets clobbered. And then to get v by itself, I can divide both sides by m. And it looks like that. The final velocity is F times t divided by m. I can plug in my numbers, and I can get 87 meters per second. So the final velocity of the ball would be 87 meters per second. Now, you could do the exact same job. You could change the momentum in a different way. Instead of having 800 newtons for 0.05 seconds, you could have 400 newtons of force for 0.01 seconds. If you double the time, you only need half the force to have the same change in momentum. All right, another example, a bowling ball is rolling to the right. So this bowling ball is rolling towards this guy, and he's got a leaf blower. He's going to try to stop it and change its direction and send it back the way it came. So it's moving to the right, and he wants to send it back to the left. Okay, so it's a 5 kilogram bowling ball. It's rolling to the right with a velocity of 3 meters per second. The leaf blower exerts a leftwards force of 2.5 newtons. How long will it take to stop the ball and reverse the speed? So we're trying to find the time. So here's my variable list. The mass is 5 kilograms. The final velocity is -1. Remember, the direction matters. So if the ball is rolling to the right at 3 meters per second and he needs it to roll to the left at 1 meter per second, this is negative and this is positive. And since the force is leftward, we make that negative. So that's my variable list, and I'm trying to find the time here. So we will start by applying the principle. That means F times T equals mv final minus mv initial, and we're solving that for T. Nothing is 0, so we can't cancel anything. But to get T by itself, I divide both sides by F, and so here's my algebraic solution. And then I can plug in my numbers and watch out for signs. The mass is 5 kilograms. The final velocity is -1. Then you've got a minus here. And then it's the mass times the initial velocity, which is positive, and that's all divided by the force, which is negative. And you're going to get these wrong if you're not careful with your signs. So when you work that all out, it turns out to be 8 seconds. So this guy's got to blow in the bowling ball for 8 seconds in order to make the ball stop and change directions. So this force, 2.5 newtons, acting for 8 seconds, will do it. Now, if he had a force of 5 newtons, if the force was twice as big, he would only need to blow on it for 4 seconds. So that's the idea. The force times the time is the change in momentum. So you're going to solve a problem set with these. So make good diagrams, make your variable list, state the plan. So you're going to apply the principle to get an equation, and you're going to solve it for something, solve it algebraically, and then work out the numbers there. Okay? All right, good luck.